Every year, over 100 million tons of banana plants are harvested worldwide. The fruit leaves the field, the bird, but the Bedia pseudostem growths, now abandoned as cemetery, completely ignored.
Despite its appearance, a banana stem is not wood. It's a pseudostem. Locked inside this moisture is something extraordinary. Long, continuous cellulose fibers march, naturally aligned by the plant's own growth geometry. At the microscopic level, banana fibers are rich in alpha smoother and require far less chemical processing to extract. This makes them uniquely suited for sustainable manufacturing. So why was this material overlooked? The answer is logistics. Banana stems are heavy, wet, and begin decomposing within hours. Without rapid processing, the fibers weaken. That changed with the rise of specialized decortication technology, machines designed not to crush or grind but to gently separate fibers from pulp. This technological shift transformed banana stems from a disposal problem into a raw material stream. Compared to cotton, banana fiber requires no replanting. Compared to synthetic fibers, it needs no petroleum. And compared to jute, it offers higher tensile length with less land use. What was once waste now competes with the world's most established materials. This is where the transformation begins. In the next phase, these water-heavy stems will be cut, sorted, and fed into machines engineered to extract value without destroying structure. The challenge is simple, but the science is not. The moment bananas are harvested, the clock starts ticking. The pseudostem is no longer supported by active nutrient flow. Inside, enzymes begin breaking down can drop dramatically, unless the stem is processed fast. Modern harvesting uses hydraulic shear cutters, not machetes. The goal is a clean basal cut. Jagged cuts create microfractures that propagate along the fibers, shortening usable length and reducing tensile strength during extraction. A full banana stem can weigh over 30 kilograms. To make transport viable, stems are sectioned into standardized lengths. This isn't just about size, it ensures uniform pressure distribution later when stems enter conveyor-fed processing lines. Because banana stems are more than 90% water, dehydration is the enemy. Industrial crates use breathable liners that slow evaporation without trapping heat. This preserves fiber elasticity while preventing microbial growth. Load sensors help operators maximize payload without crushing the stems underneath. Compression at this stage permanently deforms fiber bundles. Most high-tech banana fiber factories are built within a short radius of plantations. The reason is simple. Every hour saved in transport preserves fiber length, brightness, and mechanical integrity. With logistics complete, the stems enter the heart of the system. What happens next determines whether these fibers will become textiles, composites, or waste once again. This is the most critical phase of the entire process. One mistake here, too much pressure, the wrong blade angle, excessive speed, and the fibers are destroyed. Unlike wood or husk, banana fiber must be separated, not crushed. The stems are fed horizontally into the decorticator using soft grip rollers. These rollers apply uniform compression, not to flatten the stem, but to stabilize it. Uneven feeding would cause torsional stress, snapping the fibers mid-length. Inside, curved steel blades rotate at carefully controlled RPM. Their edge is blunt by design. Sharp blades cut fibers short. Blunt edges create shear force, scraping away soft pulp while leaving long cellulose strands intact. Speed is everything. At low RPM, pulp clogs the system. At high RPM, centrifugal force fractures fibers. Most machines operate in a narrow window, typically between 700 and 900 rotations per minute, optimized through material testing. Water isn't just for cleaning, it's a mechanical tool. Controlled water flow reduces friction, prevents heat buildup, and carries away dissolved sugars and sap. Heat is dangerous here. Above certain temperatures, cellulose chains weaken. What emerges is raw banana fiber, long, flexible, and intact. These fibers can exceed 1 meter in length. Their continuity is what gives banana fiber its value in textiles and composites. Nothing here is just pulp. Rich nutrient is diverted for secondary use. In many factories, it becomes biofertilizer or biogas feedstock, closing the waste loop. At this stage, the fibers are mechanically separated, but chemically unstable. Natural gums and sugars still coat the surface. To make them usable, purification must follow. Freshly extracted banana fibers look clean, but they're not. Their surfaces are coated with natural gums, sugars, and pectin. Left untreated, these substances cause fibers to stiffen, darken, and break during spinning. The fibers enter a multi-stage washing line. Each drum is designed to agitate without entangling. The motion mimics hand washing, but scaled up, precisely controlled, and continuous. Instead of harsh chemicals, high-tech factories use enzymes. These biological catalysts target pectin and hemicellulose, breaking bonds without attacking the cellulose backbone. The result is cleaner fibers with preserved strength. Degumming only works within a narrow chemical window. pH is carefully held between mildly acidic and neutral. Temperature stays below critical thresholds, because excessive heat weakens cellulose chains at the molecular level. Agitation is subtle. Too much motion causes fiber knotting. Too little leaves residues behind. Drum perforations allow dissolved gums to escape while fibers remain suspended and untangled. Final rinsing uses a counterflow system. The cleanest water meets the cleanest fibers, reducing total water consumption while maximizing purity. It's fluid dynamics applied to sustainability. Used water isn't wasted. Solids are filtered out, enzymes neutralized, and water reused. This closed-loop system reduces environmental impact and keeps operating costs low. What emerges now is purified fiber, chemically stable, flexible, and ready for controlled drying. Structure preserved, strength intact. The most delicate work is complete. After washing, banana fibers are chemically clean but physically vulnerable. Too much moisture invites mold. Too little, too fast, and fibers become brittle. Drying isn't about speed, it's about control. Industrial banana fiber dryers look simple, but inside they are finely tuned environments. Temperature, humidity, and air velocity are continuously adjusted to protect cellulose structure. Instead of blasting heat from above, air is pushed laterally across the fibers. This prevents surface drying while the core remains wet, a common cause of internal stress fractures. Sensors continuously read residual moisture. When levels drift outside tolerance, airflow and temperature adjust automatically. This closed-loop control ensures consistency, batch after batch. Drying is followed by alignment. Rollers apply light longitudinal tension, straightening fibers without elongating them. Alignment improves spinning efficiency and reduces breakage later. Laser scanners measure thickness and uniformity at thousands of points per second. Fibers outside tolerance are flagged automatically, long before they reach final production. Based on moisture, thickness, and alignment, fibers are graded. Finer fibers head toward textile use. Coarser ones are redirected to ropes, mats, or composites. Nothing is wasted, only reassigned. At this point, the fibers are stable, sorted, and standardized. What happens next depends not on nature, but on engineering choice. Once graded, banana fibers don't follow a single path. Their destination depends on length, fineness, and flexibility. Each application demands a different mechanical approach. For textiles, fibers must be opened and parallelized. Carding machines untangle bundles without tearing them apart, critical for a material naturally stiffer than cotton. Banana fiber spinning operates at lower speeds and higher tension sensitivity. Too much twist snaps the fiber, too little and the yarn lacks strength. Sensors constantly correct for both. Pure banana fiber is strong, but blending improves softness and durability. Ratios are calculated based on end use, balancing natural stiffness with flexibility. For ropes, thickness matters more than finesse. Banana fiber's natural length gives it an advantage, producing durable, biodegradable cordage without chemical reinforcement. In composites, banana fiber becomes reinforcement. Its role is structural, absorbing stress while reducing plastic content. Fiber orientation here determines final material strength. Controlled heat and pressure lock fibers into their final form. Temperatures stay carefully below degradation thresholds to preserve cellulose integrity. From waste to working material, the transformation is complete. But before anything leaves the factory, it must prove itself.
Let's cut these specimens to size. Right, I'll get the shears. Now to label them for the tests. Perfect.
Tensile tests measure how much stress fibers can withstand before breaking. Banana fibers often exceed 500 MPa, rivaling synthetic alternatives. Sensors record elongation, elasticity, and failure points in real time. Durability isn't just strength. Abrasion tests simulate years of wear in minutes. Banana fibers maintain surface integrity due to their natural cellulose alignment, unlike weaker plant fibers. Humidity affects performance. Testing under controlled moisture and temperature ensures fibers won't warp, shrink, or rot during shipping or storage. Maintaining cellulose integrity is critical. One of banana fiber's key advantages is sustainability. Biodegradability tests confirm fibers break down naturally without leaving microplastics. Carbon footprint analysis further validates environmental benefits over synthetic alternatives. Data drives decisions. Automated systems aggregate results, flag inconsistencies, and optimize production parameters for each batch, ensuring every fiber meets exacting industrial standards. Even rejected fibers have value. Pulp can become fertilizer, feedstock, or biogas. Waste loops minimize environmental impact, making the factory as sustainable as the product itself. After rigorous evaluation, banana fibers are ready for the world, verified, standardized, and sustainable. Every strand tells a story of scientific precision and environmental responsibility. From tropical plantations to international markets, banana fibers now compete with traditional textiles, ropes, and composites. Efficient logistics ensure they arrive without moisture loss or structural damage. Packaging isn't cosmetic, it's engineering. Moisture-controlled wrapping prevents fiber degradation, while sensors guarantee that every bundle meets strict export standards. These fibers travel across continents, entering markets for sustainable textiles, eco-rope, and composite materials. What was once agricultural waste now supports international supply chains. The next generation of banana fiber factories is automated and AI-driven. Predictive sensors adjust machinery in real time, optimizing yield, reducing breakage, and ensuring uniform quality across millions of fibers. Banana fibers are no longer niche. They are integrated into circular economies. Fashion, construction, and packaging industries now use them to reduce reliance on synthetic materials. Compared to cotton or synthetics, banana fibers require less land, water, and energy. Their biodegradability eliminates microplastic pollution, proving that industrial innovation can coexist with environmental stewardship. Looking forward, banana fiber is more than a material, it's a platform for innovation. Lightweight composites, biodegradable textiles, and eco-rope solutions point to a future where industrial waste is a resource. From waste to wealth, from field to factory, banana fibers, in every strand, lies a story of innovation and a future of sustainability.